Hello, in this lecture, we'll define rotation index of a closed curve. But before that, we'll continue with the sign curvature defined in the last lecture. So we'll prove that suppose you are given a real valued function k, so then there exists a curve such that the curvature at each point of the curve is given by that real valued function. Okay, so let me first state that theorem. So let us take, so let k be any smooth function so this k is defined on the open interval AB. So then there exists a unit speed curve gamma defined on that open interval. So this gamma also it lies in R2. So whose signed curvature is, so signed curvature at gamma s is given by k of s. Okay. All right. And further, so if gamma tilde is any other curve is any other unit speed curve whose signed curvature is given by the function k. So then what is the relation between this gamma tilde and gamma? So then there exists a rigid motion in R2 such that that rigid motion it takes this gamma tilde to your gamma, or there exists a rigid motion m such that m of gamma is equal to gamma tilde. So there, so then there is a rigid motion. So rigid motion means it is an isometry of R2. So isometry means it preserves the distance function of R2 such that this gamma tilde s is equal to m of gamma s for all s belonging to this interval AB. Okay, so now how to prove this thing? So proof. So fix some s naught in this interval AB. Okay, and let us take any element s in this interval AB. Okay, and now So uh, we already know the sign curvature, which has to be Ks. Okay. So then define. So define phi of s. So this equal to the integration s naught to s Ks ds. Okay, so take this integral. So this phi, in fact, it will be the turning angle of the curve, unit point curve, which we are going to obtain. Okay, and now we are going to define the curve. So define, so gamma s to be equal to uh, integration, again integration, s naught to s cos phi s ds, comma s naught to s sin phi s ds. So this is my definition of this gamma. Okay, and this gamma, it is differentiable, and because k is smooth, phi is will be a smooth, so gamma will also be a smooth curve. Okay, and what is my gamma dot s? So this is equal to cos phi s comma sin phi s. So this implies that norm of gamma dot s is equal to 1. Okay, so therefore this gamma is a unit speed curve, and uh, so what is my d phi ds here? So this, from here, it is equal to ks. Okay, so this equal to ks. So uh, and so this d phi ds. So this, in fact, it gives you the this signed curvature of the curve gamma. Okay, so therefore, by the previous theorem, the signed curvature of gamma is of gamma at gamma s is ks. Okay, all right. And now let us to the second part. So we have another curve gamma tilde. Okay, so whose sign curvature is also k. So then what we have, so let phi tilde s be the smooth turning angle for gamma tilde. Okay, so then so gamma tilde dot s is equal to cos phi tilde s comma sin phi tilde s, this. Okay, and so this gamma tilde s, again you can integrate this thing. So what we'll get, so we'll get this integration s naught to s cos phi tilde s ds, comma this integral sin phi tilde s plus this gamma tilde s naught. Okay, so you'll get this thing, and this ks, so it is given to be d phi tilde ds. Okay, so therefore this phi tilde s, so this is equal to integration s naught to s ks plus phi tilde s naught. Okay, so we have this thing, and so what was the definition of this phi? Phi was the integral s naught to s ks ds. So this is my phi s plus phi tilde s naught. Okay, so we have this thing here. Okay, and now what you do? So this put this phi tilde obtained by this equation to this equation. Okay, so you do this thing. So what you'll get? So gamma tilde s is equal to gamma tilde s is equal to integration s naught to s cos phi s plus phi tilde s naught ds plus comma integration s naught to s sine phi s plus phi tilde s naught ds plus phi tilde s naught. Okay, so we have this thing here, and now what you take, so TA with our translation denotes the translation. Yeah, so in this above equation, so this is not phi tilde, this is gamma tilde s naught. So T A bar, this is a translation by vector A bar. So this is an isometry of R2, and rho theta be the denote the rotation by an angle by the angle theta. Okay, so then if I take, so let A bar to be equal to gamma tilde s naught and theta to be equal to phi tilde s naught. So if I take this thing, so then this gamma tilde s, so this is equal to composition of this translation followed by rotation applied on this gamma s. Okay. All right. So therefore, this gamma tilde is obtained by a rigid motion, and that rigid motion is a composition of translation and rotation. Okay. All right. And now let me define what you mean by rotation index. Okay. All right. So first, let me prove this thing. So this I have stated in the last lecture. So proposition. The total signed curvature of a closed planar curve is an integer multiple of 2 pi. Okay. So what is the proof of this? Okay. So whenever I uh, take the sign curvature of a planar curve, so by uh, default, I assume that that curve is smooth and also, yeah, so that curve is smooth and also regular. Okay. Okay. So let me write down here. So this planar, smooth, regular. Okay. So let us take, so let gamma be a closed planar curve, and so and the parameterization is arc length parameterization. Yeah, so this parameterization is arc length parameterization we can take. Okay, so this gamma, it is a closed planar curve, and this is the arc length parameterization. So therefore, it will be a. So this implies that. So this implies, so gamma is a unit speed curve. Okay, so let phi be the turning angle of gamma. Okay, so then the signed curvature of gamma at gamma s is given by k is equal to t phi ts. Okay. Okay. Now, so what will be the total signed curvature? The total signed curvature uh, of gamma s will be the this integration. So 0 to L ks ts. Okay. All right. Okay. And so this gamma, so it is a unit speed curve, and phi we have taken it to be the turned in angle. So therefore, so this gamma dot s, so this will be equal to cos phi s comma sin phi s. Okay, all right. So now, so observe that, so this gamma, so it is something like this. It is a closed curve. So this gamma, it is defined on the interval 0 to L. So it is a closed curve, means that gamma 0 is equal to gamma L. Okay. And now if I take the interval, so if I take this interval, suppose this point is my 0 and this is my L. So on here, So this gamma is defined. Okay. So we can extend the definition of gamma on whole real line. So how do you do this thing? So this is equal to L plus L. So you take any point here. Let us call it to be U. So then, so what is my, okay. So define this gamma tilde R2 R2 as follows. Okay. So gamma tilde uh, of S is equal to gamma S. So whenever S it belongs to your 0L. Okay. And suppose this S now it belongs to, suppose in this interval. So S it belongs to L comma to L. Okay. So then S uh, yeah, S minus L, so it will belong to again 0 comma L. Okay, so gamma is defined on that thing. So the on this interval 0 to L, gamma is defined. So therefore here we can define gamma of 0 minus L, gamma of S minus L, so that you can define. Okay, and you can continue in this process. All right, so so in this way, so this gamma tilde is defined. So gamma tilde is an extension of gamma. Okay, and this gamma tilde S plus L will be always equal to gamma tilde S. Okay, so this is always true. And now if I take the derivative of this gamma tilde with respect to S, so what we'll get? So gamma tilde dot S plus L will be equal to gamma tilde S. Okay, so what is the purpose of doing this extension? So now you put S equal to 0. So put S equals to 0. So what you'll get? Gamma tilde L is equal to gamma tilde dot 0. So gamma tilde dot L is equal to gamma tilde dot 0. Okay. So, okay. So now, so what this will imply? So this will imply the following. So gamma tilde dot L. So this is equal to cos phi L comma sin phi L, and gamma tilde dot 0 is equal to cos phi 0 comma sin phi 0. Okay, so you have this thing here, and because these two velocity vectors are same, so this implies that cos phi L is equal to cos phi 0 and sin phi L is equal to sin phi 0. Okay, so therefore from here, so this phi L minus phi 0 is equal to 2n pi. Okay, so therefore this total sine curvature, yeah, so this total sine curvature, yeah, so this total sine curvature is equal to, from here is equal to integration 0 to L d phi ds equal to multiplied by ds. So this is phi L minus phi 0. So therefore it is equal to 2n pi. Okay. So therefore we have proved that the total sine curvature of gamma, so this is equal to 2n pi. Okay, so this n, it is an integer. Okay, all right. So what is the definition of rotation index? So this number, the number n is called the rotation index of the closed curve gamma. Okay. Okay. So let us do one example. Okay. So let us take this curve. So let gamma s equal to 1 plus cos s comma sin s. S is varying from 0 to pi. This is again equal to minus 1 comma minus cos s comma sin s when s is varying from pi to 3 pi, and it is equal to again 1 plus cos s comma sin s when s is varying between 3 pi and 4 pi. Okay. So what will be the trace of this gamma? So this is my xy plane. Okay. So s, if I put s equals to 0, so gamma 0 is equal to uh, gamma 0. So this is equal to 2 comma 0, right? So gamma 0 is equal to 2 comma 0. So the curve, it starts from 2 comma 0. And what is my gamma of this pi? So this is 0 comma 0. So cos pi is minus 1. So therefore gamma of pi is 0, 0. So the curve starts from here, goes like this. Okay. And so what is gamma of 3 pi? Yeah. So this again, it should be again 0, 0. And yeah, so instead of taking gamma 3 pi, so let us observe what is gamma of 2 pi. By the definition, it is equal to minus 2 comma 0. So it comes here. Okay. So yeah, so the curve now it goes like this. Yeah. And finally, for this interval 3 pi, to 4 pi. So what we have? So we have like this. Okay, so this is my curve, trace of the curve. Okay, so now how do you find rotation index of this curve gamma? So gamma, clearly it is a unit speed curve. So in fact, if I take gamma dot s, so what you'll get? So it will be minus sine s comma cos s when s is varying from 0 to pi, and this is equal to sine s comma cos s. S is varying from pi to 3 pi, and this is equal to again minus sine s comma cos s when s is varying from 3 pi to 4 pi. Okay, so this is my gamma dot s. Okay, yeah, and here, so what you can do, again you can compute this gamma double dot s. So gamma double dot s is equal to minus cos s comma minus sine s when s is varying from 0 to pi and s is varying from 3 pi to 4 pi, and it is equal to uh, cos s comma sine s when s is varying from pi to 3 pi. Okay. So therefore, so the curvature, so what will be the curvature? So this is equal to plus 1. So this is equal to plus 1 whenever s is varying from 0 to pi and s is varying between 3 pi and 4 pi. And it is equal to minus 1 when s is between pi and 3 pi. Okay, so therefore, what will be the total sine curvature? So the total sine curvature is 0 to pi plus 1 ds plus plus pi to 3 pi minus 1 ds plus 3 pi to 4 pi plus 1 ds. Okay, so this is equal to then pi minus 2 pi plus pi, so which is equal to your 0. Okay, so therefore the rotation index is of gamma is equal to your 0. Okay, so now let me end this lecture with a statement which we are not going to prove. Okay, so this theorem is due to Hopf. It is named Umlaufsers. It is a German word. So the theorem states the following. So let gamma be a regular simple closed curve. So then the rotation index of gamma is plus minus 1. So it can be either plus or minus 1. So now what is the meaning of simple closed curve? Yeah, so this simple closed curve, so I have taken in R2. So a curve gamma defined on this closed interval is said to be simple closed curve if gamma A equal to gamma B, and so gamma restricted to the open interval is injective. Is an injective map. So it says that, so this gamma, apart from the endpoints, it doesn't have any self intersection. Okay. So for example, so this is a simple curve. Okay. And if I take this curve, this closed curve, okay, it is not simple. So this is a simple closed curve. And this is a not simple. Okay, so what proved that if I take a regular simple closed curve in R2, so then the rotation index is either plus 1 or minus 1. Okay, so we'll stop here.